Chapter 4, types of chemical reactions and continuing stoichiometry. I think we were finished with stoichiometry. So you never finish with stoichiometry. Come on, helps to turn it on. There we go. Okay. When we talk about solutions, for our purposes, most of our solutions, I mean, we've identified bunches of different types of solutions. All you need is a homogeneous mixture. That's a solution. But we're going to focus, for the most part, on aqueous solutions because they're central to most chemical reactions and particularly to biochemical reactions. And it all has to do primarily with the power of water to act as a solvent. So this is a model of a water molecule. And you can see from the composition, it's only one oxygen molecule and two hydrogens. But the neat thing about it is that the molecule itself is bent. If you use the oxygen as the apex, central atom's apex of the angle, then the oxygens, instead of being like that, are like that. And that has an effect on the way the molecule behaves around other molecules. And we haven't talked about electronegativity yet, but we will later on. The short story is that the oxygen has a much stronger pull on electrons than hydrogen does, even though these are covalent bonds. In other words, electrons are shared. You get a redistribution of electron density toward the oxygen, and that gives it a slightly negative charge. That leaves the hydrogens deficient in charge. Now, this is not a complete charge. That's why I used a little delta, Greek delta. It's only partial. What that does is it makes the molecule polar, which means this side is the negative side and this side is the positive side. So it wants to interact electrostatically with other molecules that are also polar. Molecules that have a distribution that gives them a positive side and a negative side, so then they'll line up negative, positive, positive, negative. And it makes the solution more likely if you can get polars together with polars. It's also very strongly attracted to ions. If you got complete ions like sodium chloride, when you put it in water, it breaks apart into sodium ions and chloride ions, positives and negatives. And the water molecules tend to accumulate their negative sides around the sodium ions because they're positive. And the positive sides around the chloride ions because they're negative. It's a process called solvation. So, many molecules, many compounds are charged or partially charged. That's why water is often referred to as the universal solvent. That's a stretch. There's some things that will not go into the water solution. And I mean, you just make your own salad dressing and you know that water won't dissolve everything. But you have to shake it really, really hard and then pour it on your salad before it separates. But it does dissolve lots of things. And we have, through trial and error at first, and now we understand why, created chemical go-betweens so that water can dissolve non-polar solutes. Those things that are non-polar will go into aqueous solution if we have a go-between. The first one that was commonly used and still is in some places is soap. Soap has a long tail as the non-polar end, and then it has a polar end. So this end is going to be slightly negative. This over here is going to be nothing, believe it or not, because this has given up a proton, a hydrogen atom with a positive charge. So that's where the positive went. I can see the wonder in your minds. If this is negative, where'd the positive go? Well, it's off by itself. Well, actually, it's not hydrogen, it's a sodium ion, if we're talking about soda, but that's another story. Anyway, this part is nonpolar, so it will dissolve itself in the oil or the nonpolar, whatever. Most clothes get dirty because of oil from your skin, primarily. And then to get that off there, you put soap in it or something like soap that will dissolve in the oil that's in your clothes. And then this part associates itself with the water. And that way water can pull the oil out of your clothes and wash it away. You know, unless you've got hard water, and then that's another subject. Then you get rings around your tub and water stains in your clothes, things like that. That's why we use detergent now rather than soap. But like I say, that's another extensive story in itself. But the point of this slide is that water is a polar molecule. So it's preferentially attracted to polar solutes. Let's see, I've got something for you. And it's right here. Are those yours?
No, there was extra.
Oh, okay.
That.
Because I saw them laying on the table when I left. And
I got mine. There's extra accidentally picked up.
okay, just plop them down.
Yeah, I'm gonna put it back.
Okay, so I've got a little movie here. Hopefully it won't be too long, but that'll help describe some of this stuff. So I've used some words that I haven't defined yet, like solvent and solute. But solvent is the major component in a mixture, in a homogeneous mixture. And solute is the minor component. So if you have, say, water, and you're going to add some sugar to it, table sugar, sucrose, add a little bit in there, stir it up. Sure enough, it goes into solution. Put a little more, goes into solution. Sucrose is unique. I would say unique. It's special in some ways because eventually you can put more sugar in that solution than you'd have water. It just keeps going into solution. But we started off with mostly water and a little bit of sugar, so we keep it that way. So even though the sugar can exceed the amount of water, water is still the solvent. And sugar would be the solute. Okay. Now, if this is an operational definition for electrolyte, Electrolyte is anything that dissolved in water will now conduct electricity. Water itself, pure water, is an insulator. It will not conduct electricity. The only way you can get water to conduct electricity, well, two ways. You can put an electrolyte in it. Now you've got mobile charges that can carry the charge from one electrode to the other, complete a circuit. The other way is to boost the voltage between the electrodes so high that you ionize the water. And if you do that, then the electricity will flow. That happened to a classmate of mine in high school. I was a teacher's kid. So I went to a private school and we got a break-up tuition. All they had to do was buy uniforms and books instead of paying the full tuition. But most of the kids there were rich, and their families had the in-town house and the out-of-town house, and some of them had cabins by the lake. And this was in Atlanta. And one weekend, one of the girls in our class went to spend the weekend at the cabin, and she made the mistake of taking a bubble bath during an electrical storm. Now, she would have been okay, except she was talking on the telephone. And this was a hardwire, a landline. Sure enough, lightning struck the pole, went down there and threw her into the ground. And she was no more. The water conducted, partly because the voltage was so high, but probably because she had some other things in the water. She may have been using salts. But the water was conductive under those circumstances. But that's an electrolyte. By definition, electrolyte conducts electricity. Now, when you get your blood work or your analysis back, it'll have a bunch of electrolytes in there. Like it'll have sodium, chlorine, potassium, calcium, and magnesium, and a bunch of other ions. Those are metabolic electrolytes. But this is a chemical definition. Non-electrolytes, of course, are those that go into solution and do not allow the solution to conduct electricity. So our previous example where we put sucrose in water, it will not conduct electricity because sucrose is not charged. It doesn't carry a charge through from one electrode to the other. It's a non-electrolyte. A strong electrolyte is one which efficiently transmits electricity through the solution. Now these are qualitative definitions or semi-quantitative. So a strong electrolyte would be something like sodium chloride. When it goes into solution, it completely dissociates into ions. Or when you put an acid in like hydrochloric acid or sulfuric acid, they completely dissociate, and everything you put in there is now a mobile ion. Those are strong electrolytes. Weak electrolytes, on the other hand, are those that you put into solution that only partially dissociate. They will go into solution because of their molecular nature and their polar molecules, and they associate with the water, but they only ionize partially. A good example of that is vinegar or acetic acid. Acetic acid is a weak acid, which means it only dissociates partially. The hydrogen ion that's attached to the molecule, only a few of them leave the molecule and make mobile ions. It will still conduct electricity, but not very efficiently. And one way to imagine is if you have a light bulb in the circuit, a strong electrolyte, the light bulb will be really bright, a weak electrolyte bulb will be very dim. Oh, got another movie.
We know from various lines of experimental evidence that solid sodium chloride consists of an ordered three-dimensional array of sodium and chloride ions. Solid sodium chloride is not a conductor of electricity. The ions of the ionic lattice are held in place by the strong ionic interactions in the solid and therefore are not free to move under the influence of the electric field. When sodium chloride is dissolved in water, it forms a solution of separated sodium and chloride ions. The presence of ions in the solution is responsible for the fact that the solution is a conductor of electricity. Substances such as sodium chloride that exist in aqueous solution entirely or nearly entirely as ions are called strong electrolytes. By contrast, an aqueous solution of a non-electrolyte such as sugar does not conduct electricity.
So, why do we bother with solutions? Well, first of all, a lot of stuff is already in solution, right? Oceans, lakes, the bodies of water. But in the laboratory, lots of useful chemical reactions take place in solution. And one of the primary reasons is that you can get the reactants close to each other. Whereas if you try to put two solid reactants together, the only place they're going to interact is where they're touching. So you won't get much activity. But if you can put them in solution, then they've got access to each other. So the reaction can proceed. So in order to describe the reaction fully, we need to know what kind of reaction it is and how much of each of the reactants are present, because that will dictate a number of things, whether the reaction will even occur or how fast it will occur. And we'll cover that in the second semester, chemical kinetics. But we also need a way to express that concentration. And one of the most commonly used units for expressing concentration is molarity. And as the name would imply, with a capital M, molarity has something to do with moles, right? Its concentration in solution is moles per liter, moles per unit volume. And I use an N for moles and a V for volume. Notice I don't put a zero up there. If I do that, then you might think it's a neutron. But that's number of moles. And the volume has to be in liters, in units of liters. Okay, so if we know there are 6 moles of hydrogen chloride dissolved in 2 liters of solution, and this is volume of solution. That's after the solution is made. That's what the volume is. So the solute that you put in there may have an influence on the final volume. And so when you make a solution for molarity, you generally use a volumetric glassware of some kind, like a volumetric flask with an arrow, and it's got a mark around here. And let's just say, for argument's sake, that's 1 liter. Well, you put a little bit of water in it. Well, we're assuming water is the solvent in this case. And then you add your solid or liquid or whatever you're going to put in there and get it in solution. And then you bring it up to the mark. Now you know that you have 1 liter of solution and not just 1 liter of solvent. So in this case, 6 moles of hydrogen chloride dissolved in 2 liters of solution is 3 molar. We named compounds already, didn't we? Yeah. Hydrochloric acid. Okay. So when hydrogen chloride is off by itself, it's a gas. So we name it hydrogen chloride. But if we write it like this, that means it's in solution. And now you name it like an acid, hydrochloric acid. Notice there's no oxygen in there, so we started the name of hydro. Just a reminder. Okay, so what do you do if you're not given the number of moles? I say with 500 grams of potassium phosphate. and we want to make up a solution that's 1.50 liters of solution, we need to know how many moles that potassium phosphate is. Okay. That's why you need to know how to write the compound. Otherwise, you can't determine the molar mass. And the molar mass is what is the conversion factor that you use to convert grams to moles. Say if we have 500 grams, and we want to go to moles, this tells you the numerator, and this tells you the denominator. So whenever you see grams and moles, probably said this before, grams and moles together in a quotient, think molar mass of something. In this case, it's potassium phosphate. So we know we have potassium, and we know we have phosphate, which is a polyatomic ion. And you look it up in your chart. Has a 3- charge. Potassium is an alkaline metal in the first column. Those are all +1s. Okay, so now you balance the charges. Okay. You need 3 of these to balance those 3 minuses. That's the formula that gives you the molar mass, potassium phosphate. So we, let me follow along here so I can see if I need to write this on the board or is it on? It's up there. Okay. So we add 3 times the mass of potassium, 1 phosphate, and 4 oxygen masses. This is the molar mass of each element. Add them together, and you end up with 212.27 grams per mole. Right. So now the grams cancel. 212 into 500 is in the neighborhood of 2, something like that. Exactly 2.355 moles of potassium phosphate. That goes in this place right here. And you're given the final volume, you want it to be 1.5 liters. So that goes in the volume part of the equation. Right? This is just equation. M equals N divided by V. It's like any algebraic expression.
How did you get the 212.27 grams?
Potassium, 3909 grams, excuse me, G9 grams per mole. And then phosphorus, which is 30.97. There's only 1 of them.
Right.
And then 4 times oxygen, which is 16 each.
Okay, I see how you did it.
And then add them together. Yeah, that's how you get the molar mass of a compound. So now we know that this solution that we've created has a molar concentration of molarity of 1.57 molar. And we use that big M because there's no element of the periodic table that's 1 M. There are lots of them with M with a small letter behind them, but no 1 M. Now, what if we wanted to find out, what was that, 1.57? I'm going to use this example. Excuse me. Molarity is 1.57 molar. Okay, in that compound, right there. What if we wanted to also say, what's the molar concentration of all the ions together? Because when it goes into solution, it breaks apart into cations and anions. Right? So in this compound, we have 3 cations and 1 anion. So we have 4 ions for every 1 formula unit. That means the ionic concentration is 4 times that. 6.28 molar ionic concentration. Now, why would we want to know that? Well, I can think of one good reason. If you're in the medical profession and you're making up a solution for to IV for your patient, and you don't give them a solution that's isotonic with their body fluids, you'll kill them. And isotonic solution, I'm not sure what it is in molarity, but I know it's 0.9%. Sodium chloride is isotonic. You just have to calculate what that is in molarity. Could do it. But that's one of the reasons you want to know the ionic concentration rather than just the molecular concentration, the formula concentration. So you don't kill people. Now, of course, most personnel don't make up their own solutions anymore. They come ready-made. But somebody's got to make them up. So whoever makes those solutions better know their chemistry. Okay, this example says that 0.25 molar calcium chloride makes 3 ions, 1 calcium ion and 2 chloride ions. So if the concentration starts off at 0.25, you still got 1 calcium per unit. That means the calcium ions are still 0.25 molar. But the chloride ions are now 0.5 molar. That means total molarity is 0.75. 3 ions at a concentration of 0.25 for the whole molecule gives you 0.75 molar in ions. That same molar concentration for sodium chloride would only give you 0.5 molar in ions. And we're going to introduce a concept second semester, sorry. It's called the colligative property. And it has to do with how many moles of anything are dissolved in the solution. It doesn't matter what they are. And they will have an effect on the freezing point of water. So that's why they put salt on the roads. You get enough salt dissolved in the water, because think of ice or snow is in flux. It's constantly going backwards and forwards between liquid and solid. And when it gets to the liquid state, it picks up those sodium chloride ions, and now it won't go back to the solid because it's not cold enough. Well, if you have more ions per mole of formula unit, your compound is more effective. It means that the freezing point of water is lowered even further. So that's why calcium chloride is much more effective as a de-icing agent than sodium chloride. It's just it costs more. So that's why they put sodium chloride on the roads instead. But if you buy it for your walkways, and especially if your walkways are made of concrete, you don't want to use sodium chloride in your walkways if they're concrete. They leave holes in. There's another chemical reaction that goes on between them, the concrete and the sodium. If you got calcium instead of sodium, then it'll leave your concrete alone and melt the ice better anyway. But it's more expensive. It's hard to find pure calcium chloride de-icing agent.
Oh, that's where we found that.
Yeah, most places that you find are going to be a mixture of calcium chloride and magnesium chloride. Now, I'm not sure if magnesium is as friendly with your concrete as calcium is, but if I get desperate, I'd try it before I'd use sodium chloride again. So I've made that mistake. When I first moved into our house, I used sodium chloride. Next spring, I was patching holes in my concrete. And of course, on most of our roads, they're asphalt, so it doesn't matter. But any concrete, sodium chloride will eat them up. And that's why. Okay, which one of these has the greatest number of ions? This is where we want Henry Ford. And I'm going to have to speed through this. Yeah. What you have to do is calculate, look at this equation. If we've got M equals N divided by V, and we're looking for the number of moles of ions, right? Greatest number of ions. Solve for this one right here. Molarity times volume. Right, let's just move the volume over here. Now we want molarity times volume. Let's see. We want molarity times volume. But we also want to take into account the number of ions each. So 0.1 times, well, that's not in liters though, is it? How many liters is 400 milliliters? Four. Close, right? How many milliliters in a liter? 1,000. So you got to move it 3 places. 0.4. Right? 1, 2, 3. 0.4. So 0.4 times 1 would be the moles of formula unit. And then sodium chloride breaks into 2, so it's 2 times that. And you would do the same thing for this one. Same thing for that one. And this one's a ringer. Because it doesn't make ions, so you just throw it out. Okay. Test taking technique. Eliminate the answers that are absolutely impossible, then work with what's left.
So VA.
Oh, I don't know. Because this has 3 ions and this one has 4 ions. Right, so you have to do the calculation. So if you do the calculation, it should be B, has the most ions of all those expressions. Now there's another possibility. Yeah, I guess I can give this to you. If you have 300 milliliters and you multiply that times molarity, what do you get? 0.1. So that would be 30.0. See, that's only 2. So it'd be 30. You don't get moles, you get millimoles. Okay. So that saves you, if you're only going to compare total amounts, doesn't matter if it's moles or millimoles, as long as they're the same apples to apples, oranges to oranges. And you can prove it to yourself. If you want to recalculate the concentration, then you take 30 millimoles, and divide it by 300 milliliters, and what do you get? Well, notice that millis in both of them. Right? So we divide milli by milli and we just cancel it. So moles divided by liters, you're back to a 10th. That's just proof that I'm not pulling your leg. Okay. That's not essential to what we're doing right now. Okay, again, solving problems, what's the question? Where are you headed? You're headed to an answer, hopefully, but you got to know what the question is. And to find the solution that contains the greatest number of moles, wait a minute, is it doing this calculation for you? No, it's not. Okay, never mind. How do we get there? Well, sometimes you can draw a picture. I don't think you need a picture for this one. Sometimes it does help. And then you calculate the number of moles of each ion. You can calculate, if you just multiply the molarity times volume, you get moles of the compound, the formula unit. Then to go to the next step, you need to know how many ions per formula unit. And you can do that dimensional analysis. Because it will give you moles of formula unit, right? And then you have, for every formula unit, how many ions do you have? Right? Maybe it's 3. So the formula units cancel and you're left with ions. So it's a dimensional analysis problem too. All right. So the point is that the solution with the greatest number of ions is not necessarily the one that has the volume, the largest volume, or the highest concentration. You've got to do the calculations to determine that. So what do we do if we're running a soil testing lab, and I've worked in those for many years, and you analyze hundreds of soils a day? You extract the soil with a specific solution, and then you send it to your technician that operates the analyzer. And they tell you the concentration of this ion and that ion and that ion and that ion, and then you generate a report and send it back to the farmer. Well, if you got to do hundreds of them a day, making up a dilute solution for extraction purposes is kind of tedious. And it may take a while for that to go into solution. So what we do is we make up a concentrated solution with the same components in the correct ratio of the components. And then when we get ready to use it, we take a certain amount of it, add more solvent, dilute it up. Now it's at the right concentration and use it. So why does it work? Okay, here's why it works. If this is the concentrated in whatever, let's just say X, concentrated solution in X, and we got a volumetric flask over here. Let's say it's 1 liter, and we want to take this concentrated X, and we want to take it down. Say this is well, say the concentration is 10 molar. Okay, we want to take it down to 0.10 molar over here. What do? We have to take an exact, as close as we can get to an exact amount over here and put it over there and then dilute it up to that volume. Okay, so if I transfer some volume over here, I'm on my way, and I've taken out a certain volume, an X volume of this solution. How many moles do I have? Well, molarity times volume, right? So this would be times 10 molarity, and that would give me moles of X. Whatever it is, moles of X. Okay. So far, so good. Okay, we're still going. So moles of X goes over here and it goes in there. So has anything changed in moles of X? Well, the same moles of X we pulled out of here is going in there. They're exactly the same. So we got moles of X over here. Okay. So now that moles of X is going to be diluted to 1 liter. So how do we figure the moles of X on either side? Well, if we have this molarity, 0.10 molar, times the total volume, which would be 1 liter, that would be the moles of X, correct? Because that's the only source of the moles going in here is from that. The rest of it is solvent. So the total volume then times the concentration of that X equals the moles of X. Okay. How about over here? Moles of X is equal to what? Well, the volume we pulled out, the volume of the concentrated solution times the molarity of the concentrated solution. That's equal to N of X. So to simplify it, let's just say this is molarity of the concentrated, and this is the volume of the concentrated that we drew out. And this is the volume of the dilute, the total volume of the dilute, times the molarity of the dilute. And they're both equal to N equals N of X. Okay. So what's that mathematical law? A is equal to B and B is equal to C, then A is equal to C. So that one is equal to that one. because they're both equal to the same thing. That's why that formula works. You just have to be sure that on one side you have the concentrated values and on the other side you have the diluted values. If you get them swapped, then your calculation's all wrong. Right? So that's why very often what I'll do is, especially if it's a complicated procedure or decimal numbers, things like that, can't do it in my head, then I'll say this. Excuse me. I'll set up a table. And then I'll put the numbers in there. I'll query the problem, put the numbers in there, and I'll find the unknown, which is usually how much of the concentrated volume do I need to put in there to get the desired concentration of the diluted. And then I'll set up the equation and solve for the unknown. That way I don't make any mistakes. Okay. That's why that equation works. Because moles equals moles. Okay, and there's a whole slide on it there. Okay. And we're using M1V1 equals M2V2. You could easily substitute concentrated for 1 and dilute for 2. Okay. So obviously, I got maybe a half hour. Yeah. If we have a 0.5 molar solution of sodium chloride in an open beaker, which of the following would decrease the concentration of the salt solution? So how do you decrease the concentration of something in solution? You either remove the solute somehow, or you add solvent. If you add solvent, you're diluting it. You're making it less concentrated. So if we add water to the solution, that'll do it. Yeah, you'll dilute it. You'll make it less concentrated. Decrease the concentration. That one's good. Pour some of the solution down the sink. No, because you're pouring part of the solute as well as the salt, and it's a homogeneous mixture. So the ratio that you're pouring down the drain is the same ratio that's left in the container. So it's not B. Add more sodium chloride to the solution. That's going the wrong direction. You're making it more concentrated. Let the solution sit out on the open air for a couple of days. That's a problem too. You're decreasing the amount of solvent by evaporation. Sodium chloride doesn't evaporate, so it's going to stay there. At least 2 of the above would decrease. No, just the 1. That's it. What's the minimum volume of 2 molar sodium hydroxide solution needed to make 150 milliliters of 0.8 molar sodium hydroxide solution? Okay. So if you're trying to decide what type of problem it is, if you want to create a solution and you've only got mass or moles of the solute and a final volume, then you have to do that simple calculation like M equals N divided by V. But if you're given a problem where you have 2 concentrations or 2 volumes and there's 1 missing, then you've got a dilution problem. We're going from 2 molar down to 0.8 molar. And the final volume is 150 milliliters. So we're looking for the volume of the concentrated solution that you bring over to dilute. All right, so we'll set it up this way. The molarity of the concentrated, the volume of the concentrated, molarity of the dilute, and the volume of the dilute. So we'll fill in our values. What's the molarity of the concentrated? 2 molar. What's the volume of the concentrated? That's the unknown. What's the molarity of the dilute? 0.800 molar. And how about the volume of the dilute? The final volume is 150 milliliters. Okay. Now notice when we do this arrangement, this is molarity or moles per liter. This is liters, and this is moles per liter, and this is liters. Okay. Where was I going with this? Oh, you've got a ratio here, and this one cancels that one, and that one cancels that one. So if we got molarity on both sides, right, we'll just leave it that way, right? That and that. But we don't have liters. Perhaps I should do. We don't have liters. We've got milliliters. Now the question is, do we need to convert to liters? And the answer is no, because it's a ratio of volume and volume. Whatever we have on one side is going to be the same on the other side, even though we've got molarity here, right? So milliliters here works just as well as long as they're both sides. That means the answer is going to come out in milliliters, as long as it's a ratio like that. If it was a simple equation, m equals n over v, yeah, you got to change it to liters, no option. But if you've got a dilution problem, you can just leave it like that. So that means if this is concentrated and this is dilute, then molarity of concentrated times volume of concentrated equals molarity of dilute times volume of dilute, which is 150 milliliters. So now we just solve for this one. We say that one times that one divided by this one, and we find milliliters of a concentrated solution that need to be diluted to make the final solution. Okay, there we go. We're using ones and twos on this, and that's okay, because that keeps them on the right side of the equation for each other. 60 milliliters. Now, does that make sense? Let's see. 60 times 2 is about 120, right? So what's 150 times 0.8? Yeah. So we're good. We're in the ballpark. All right. What are major types of chemical reactions? This is sort of a qualitative assessment. It helps to understand what type of reaction you're dealing with for a practical approach to using the equation or using the reaction, or for safety reasons. I mean, if you know it's going to be a combustion or it's going to be a highly exothermic reaction, you may want to take extra precautions. So, major types of reactions: precipitation reaction. So what's a precipitate? If you put two solutions together, and they are solutions, right? A homogeneous mixture, say two aqueous solutions, they've got two different compounds in them. Put them together, now they have access to each other. So they're going to interact. The ions are going to interact. Sometimes you get the cation from one and the anion from the other together, and they don't like solution. They're just going to go drop right out. That's a precipitate. Acid-base reaction. You get an acid together with a base, and what do they do to each other? They neutralize, right? And it depends on how much one is with the other one and what the nature of each one is as to whether the ultimate reaction, the outcome, is acidic or basic. Oxidation reduction. We'll have to go into this in a little more detail. Anytime you see oxidation reduction or redox, we're talking about electron transfers. So during the reaction, electrons must move from one species to the other. Now, sometimes reactions are multiple types. They can be classified multiply. A combination reaction or a synthesis, when you put two simple chemicals together and make a more complex one. The best example is one element plus another element makes a compound. That's a combination reaction. A decomposition is just the other way around. You take a complex and make it simpler. A single displacement reaction. You have, say, an element there, and you have a compound here with two ingredients, and this A replaces that B. So AC plus B. That's a single replacement. Okay. Example. This is hydrochloric acid, and you put zinc in the water. You're going to have zinc chloride plus hydrogen gas. Double displacement or double replacement reaction. That's where you have an AB and a CD, and they just swap partners. So this would be CB and plus AD. And a great many of your precipitation reactions follow this pattern. And then combustion. A combustion reaction needs, you have to have at least one, this reactant has to be there. Oxygen gas. Then you have something here and it yields products. But that oxygen must be there to be a combustion. All right. So a double displacement, we talked about that. Precipitations often form, in fact, the presence of a precipitation from a double replacement reaction is what we would consider the driving force for the reaction. Consider what you've got before the reaction. You got two separate solutions with their ionic compounds in solution. You add them together and they form a precipitate out of the combination of one of the cations and the anion from the other one. Okay, what are they doing? They're effectively removed from the reaction environment. And the reaction is going to keep trying to fill that void, right? As you remove those, it's going to keep reacting and remove more and more and more and more. That drives the reaction toward the precipitation or toward the product side. Here's an example where you have barium nitrate and potassium chromate. Barium chromate is insoluble, but potassium nitrate is still soluble. So all the potassium ions and all the nitrate ions still happy, they're in solution. But the barium and the chromate, they combine and they drop out of solution right here. Now, how do we know which ones will do that? Let's see. In your review document, I think it's in there. If you look on the back side of it, yep, this back page right here. This gives you solubility for the various cations and anions, most of the ones that we're going to encounter. So across the top, you have the cations, and down the left-hand side, you have the anions. And we don't read maps for mileage anymore, do we? We just stick it in the app and it tells us how far it is. Used to be, you had on every map, you had this chart, and you looked up the city you're at on one side, and then you go across the other side or across the bottom, and you find the city you're headed to, and you follow where they meet. And where they meet is the mileage. This is similar to that. Wherever they meet, is that compound soluble or not soluble? If the square is grayed out, it's insoluble. And if it's clear, it's still in solution. There are rules to go with that. But I generally don't require my class to memorize them. I'll mention them as we go because I've used them for so many years. It's kind of second nature, but learn how to use that chart and you should be fine. Okay, oops, precipitate silver chloride. All right, so we can speak of some compounds as soluble, and we have add a suffix to them in parentheses of AQ for aqueous. Insoluble, we use an S. It's important to remember because we're going to encounter this situation in second semester. Insoluble can often mean slightly soluble. These are general rules. Soluble means, very soluble, like lots of it goes into solution. Insoluble can mean none of it goes into solution, which is rare, or just a little bit of it goes into solution, and we call that insoluble. But in the second semester, we learned how to calculate how much actually goes into solution, and it's usually very small amounts. But important to understand. These are the rules I talked about. And if you want to learn these rules, they're set up so that the ones above, if you need a tiebreaker, the one above wins. So if you've got a situation where this one is a possibility, nitrate salts, or this one is a possibility, most chlorides, bromides, and iodide salts are soluble, this one wins. Okay. The one above always takes precedence. So which of the following ions form compounds with lead 2+ that are generally soluble in water? Well, we could go back to the rules, or we could use our chart. Right? So you take that chart and you follow it along. Lead. So we only have to locate lead. And lead is way over here on the right-hand side. And then you just go down. Right? So nitrate, chlorate, perchlorate, and acetate are all soluble. None of those are up there. How about chloride? Lead 2 chloride. Oh, it's insoluble too. So which are generally soluble in water? Well, first of all, that's a ringer. Right. 2 cations don't form a compound. So you throw that one out. Lead 2 sulfate, chloride, and sulfide are not soluble. Oh, here's one. Nitrates. Remember that first rule? Let's see. Most nitrates are soluble. And as far as we're concerned, all nitrates are soluble. So that's the only one that's soluble out of that bunch. The rest are insoluble. Okay, when we write an equation, we can, this form is the molecular equation or the formula equation. That's more accurate because molecules bind atoms together by covalent bonds, and they don't break apart readily. But ionic compounds, as a formula unit, will break apart in solution. So, but it's kind of grandfathered in. You can use either one, formula equation or molecular equation. You'll probably hear me using this one more often. We write it in such a way that the formula unit for one compound and the formula unit for the other compound are on the reactant side, and they're both in solution. They're both AQ. And then the reaction takes place and a double replacement occurs. Sodium and nitrate together, and then silver and chloride together form the other compound. So this is one of those equations where we don't tell you the outcome. We give you the reactants and you got to figure it out. This is a situation where you just swap partners. Say the cations, this cation goes to the other anion, and this cation goes, that anion goes to this cation. And then you say, all right, which ones are soluble? Well, these are given soluble. You look up this one, sure enough, silver chloride is a solid. Sodium nitrate, it's still in solution. So that is the molecular equation, and you balance it. In this case, it's already balanced. Then you say, but in reality, those aqueous compounds, they're broken apart into ions. So they should actually look like this: silver ions in solution, nitrates, sodiums, and chlorides. They're all in solution. But silver chloride is still a solid, so it stays here. Now on the product side, the sodium and the nitrate are still in solution. So that's a complete ionic equation. Okay. So if we want to know what's really going on in the equation, what's the important stuff, you get rid of the spectator ions, the ones that didn't do anything. Right? Sodium and nitrate are the same on both sides. Just cancel them out, because they're not part of the reaction. Well, they're there, but they're not part of the driving force for the reaction. So once you cut them out, all that's left is the silver reacts with the chloride to make silver chloride. That's the net ionic equation. Okay, and that's the one we're interested in. If we were going to conduct an experiment in the lab, and for some reason I didn't have any sodium chloride on the shelf, right? We just call off the lab. Not if I've got some potassium chloride. Potassium would be a spectator along with nitrate. So what I really want is that chloride ion. So if I can get that chloride ion in there in the right molar concentration, which would take a little calculation, then I can carry out this reaction right here, and it doesn't matter what the cation is that's paired with the chloride. Those are spectators. Here's another example. Cobalt 2 chloride here reacts with sodium hydroxide to yield cobalt 2 hydroxide, solid. Most hydroxides are insoluble. And sodium chloride, which is soluble. That's the formula equation, and it's balanced. Okay. So when we come down here, we got to take into account those coefficients and subscripts. So here we have one cobalt ion. There it is, 2+ ion. But we have 2 chlorides there. So we need a coefficient for the chloride right here. We don't keep the chloride subscript down here. It comes up here. We have 2 chlorides now in the solution. we have 2 sodiums and 2 hydroxyl. Right there. Then over here, that stays the same. We still have 2 sodiums on this side and 2 chlorides on this side. So we cancel the chloride, cancel the sodiums on both sides, and this is our net equation right here. Okay. You have a couple of 3 examples in review documents. Give you some practice. So what do we do first? Be sure you write your compounds correctly. If it's a word problem, be sure you write those compounds correctly and put them in the reactant or the product side. Then balance the equation with the molecules in place. Then split everything apart into ions on the reactant side. And then on the product side, ask yourself, well, you've already asked yourself this with the molecular equation. Ask yourself, is there a precipitate? And then you mark that one as a solid, and it doesn't change when you go to the complete ionic equation. And once you've got the complete ionic equation written correctly, then you cancel the spectator ions, and that's your net equation. And I got 7 minutes to finish this before I start losing my audience. And let's see. And I got a few more slides. So if you have to go, go. So we did stoichiometry in the last chapter with just masses. We had to convert mass to moles before we could move anywhere in that equation, correct? Has to be moles. The same rule applies for solution chemistry. You've got to convert your reactants into moles before you can find out anything about the other reactants or products. Okay, but you do it differently because now we don't have solids, we don't have pure substances that we use molar mass for, we have a solution. So we have to calculate the number of moles using what we've learned about solution concentrations. All right. Well, okay, so there's your chart, solubility chart. And there's the rules down here, just in case you want to look them up. So in this case, we have 10 milliliters of 0.3 molar sodium phosphate solution, and we add it together with 20 milliliters of 0.2 molar lead 2 nitrate solution. And first of all, we say, will a precipitate form, and then what mass of precipitate will form. And so what you have to do, since this is a word problem, you've got to write the compounds correctly. We're reacting sodium phosphate. Right? 3 minus, 1 plus, we need 3 of those. This is an aqueous solution. And lead 2 nitrate. So lead has a 2+ charge, and nitrate has 1- charge. That means we need 2 of those. That's an aqueous solution. Now, what happens? Right, that's all it tells you. In addition to the concentrations and the volumes, we'll put those in a minute. We're going to balance the equation first. This one replaces that one, and that one comes over here. So now we have lead 2 phosphate. This is a 3- charge, and that's a 2+ charge. So how do you balance that? How do you write that one correctly? When you got an odd and an even charge, cross multiply. Take the 2 over here and the 3 over here. And check yourself. 2 times -3 is balanced by 3 times 2+. So we're good. Now, is this one soluble? You can look it up. It's insoluble. Right? That's a solid. And then we have what's left over. Sodium nitrate. And remember, that's a -1, that's a +1, we're good. All nitrates are soluble. Plus, all alkali metals are soluble too. So now we got our solid. We need to balance the equation. we set up our budget. You know, if you're uncomfortable with doing it on the fly, then set up your budget. And remember, you've got polyatomic ions here that don't change on either side. So you can use those as balancing units. You don't have to split out the elements for these. Just put sodium, phosphate, lead, nitrate, and balance them that way. But most of these double replacement reactions are easy to balance, and you don't always have to do a budget. We see that we've got 3 sodiums here. Let's make 3 sodiums there. That makes 3 nitrates. But we got 6 nitrates, excuse me. Yeah, we got to go up. We need 2 of these and 6 of these. So that's 6 nitrates, 6 sodiums, 2 phosphates, 2 phosphates, and we need 3 leads. Is that right? I might have to do a budget. Let's see. Is it already balanced? So No, I'm gonna have to balance it. So let's do it. Sodium, phosphate, lead, and nitrate. So we got 3 sodiums here, 1 phosphate. Did I write these correctly? Yeah, that was right. 1 lead, 2 plus. Yeah, that's right. Excuse me, 1 lead, 2 nitrates. On this side, we got 1 sodium. We got 2 phosphates. Lead. We got 3 leads, and we got 1 nitrate. Okay. So where do we start? Let's start with lead. Let's make 3 leads here, so that the leads will balance. Now we got 6 nitrates. Okay, so we need 6 nitrates over here. But that gives us 6 sodiums. Okay, so now we need a 2 in front of here that gives us 6 sodiums, 2 phosphates. Oh, and we're balanced. So 2, 3, 1, and 6 are the coefficients. Now we've got a balanced equation. We can put the rest of that information in. 10 milliliters of 0.3 molar. 10 milliliters and 0.3 molar are reacted with 20 milliliters of 0.2 molar. Okay. What precipitate forms? We've already answered that. Lead 2 phosphate actually forms. Oh, okay. So combined solution. Those are the ions in solution. What are they? There's lead 2 phosphate. Okay. And then balanced our equation. Oh, there it is. Here's the 3 lead nitrates. Here's the 2 sodium phosphate. There's 1 lead 2 phosphate. And there's 6 sodium. So we balanced it correctly. What are the moles of reactants present in solution? Now, here's the thing you have to consider. We've got exact amounts of this reactant and that reactant. So when you see that, you should say to yourself, limiting reactant. One of those is going to run out first. So we got to decide which one is the limiting reactant. So how many moles of this? Well, molarity times volume is moles, correct? That's how we get the moles in this case. Not molar mass, but molarity. So if we multiply this one times this one, we get what? 3 millimoles. Right? Milliliters times molarity. How about this one? This one has 4 millimoles, right? Okay. Now, how do we tell? It wants to know, let's go back. It wants to know what's the mass of the precipitate, right? So if we're going to find out which one produces the least amount of precipitate, that's where we're headed. We convert this millimoles to that millimoles, and this millimoles to that millimoles, and we say, which one is the smallest? That's the one that runs out. And if we do that in that fashion, we are actually calculating the moles of this, and then it's one step further to the mass. So if we say this many millimoles is related to let's see, lead to phosphate versus sodium phosphate, the coefficients tell us the conversion factor. That's 1, this is 2. So 2 into that is 1.5 millimoles of that product. We do the same thing with this one over here, only this one has lead to nitrate on the bottom and lead to phosphate on the top. So this one's still 1, and this one is 3. So 3 into 4 is what? 1.33 millimoles. All right, so which one produces the least amount? That one does. That's the limiting reactant. So 1.33 millimoles of this product here is the molar amount that we get. We got to convert it to mass. All right, so we got millimoles. How do we make millimoles work with grams per mole? We have to convert it to moles, don't we? Okay, here's the easy way. What does that milli mean? Milli means 10 to the minus 3. That many moles. Okay. So now we need the molar mass of this thing right here. Right. I need a calculator for that. So lead. Lead is 207.21. 207.21 times 3. 2 times phosphorus, which is 30.97. Add them together. And then 8 times oxygen. So 16 for each oxygen. And 8 times that, and add those together. And I get 811.57 grams per mole. So the moles cancel, and that times 1.33 with an exponent of minus 3. And that's 1.08 grams. And let's see if I did it right. Come on, here we go. Come on down, come on down. Okay, there's the moles of each one of ours. We did those. Then we find the limiting reactant. We find 1.5 for this one, and we find 1.33 for that one. So we convert it. Let's see, there it is. So here's where I added that milli equivalent right there. And there's the molar mass. So I was off a little bit here, 0.57. disagree, but rounding to three places is 1.08 grams of product of the precipitate. Now that's theoretical, right? We're still theoretical in this equation. Recovery losses, reaction inefficiency, those types of things. You could end up with less than 100%. The more likely you would when you try to recover it. But we're not considering that for this discussion. The percent yield that we discussed at the end of the last chapter. All right, what's the concentration of nitrate ions left in the solution after the reaction is complete? Well, what happens to the nitrate ions? Nothing. They're still in solution, aren't they? Okay, so we have the same number of moles of nitrates. This is 4 millimoles of that compound. How many millimoles of nitrate do you have? 2 times that, correct? So we have 8 millimoles of nitrate. What's the volume? Well, now the volume, assuming the volume hasn't changed due to our reaction, the volume is 10 plus 20 is 30 milliliters. Okay. Here's another trick. If you divide millimoles by milliliters, you get mole parity. So let's say 8 divided by 30 is 0.27. 0.27 molar nitrate ions. Oh, there it is. This one takes a little more work. Concentration of phosphate ions. Okay. So what you've done is you've used all of this iron up. There's no iron left in solution. It's all captured in this phosphate. But this is excess. Remember, if one of them is limiting, the other one is excess. So we do have some phosphate left over in solution. What we have to do is say how much phosphate was used up to make that. Well, let's see. We had 1.33 times 10 to the minus third moles, which is 2.66 times 10 to the minus third moles of phosphate. Everybody see how I got that? Moles of phosphate used. Right, because this says how many moles of that product, but we got 2 of these ions per each, correct? So that means 2 times this is how many moles are in that. Where did they come from? They came from over here. So how many moles did we start with? Well, we had 3 millimoles, or 3, and there's only 1 per molecule, right? So 3.00 times 10 to the minus 3 moles is what we started with, and we used up this much of it. So we've got 0.34, right, times 10 to the minus 3, or 3.4 times 10 to the minus 4 moles of phosphate remain. Divided by that same volume. Divided by, well, now I'm in moles, so I have to change that to liters, which is 0.030 liters. Divide that into 3.4 by 3.4 exponent minus 4.03. So I get 1 plus 2. There it is. And we chopped off that last 3 out there. Okay. That's how much phosphate you have left in solution, because we used some of it for that, but we left some of it behind. Okay. All right. Acid-base reactions. We've been spending all our time on precipitation reactions. And we're not prepared to go into a whole lot of detail with acid-base reactions. More of that comes in the second semester. But what we can say is when an acid reacts with a base, say, let's keep it simple. Hydrochloric acid reacts with sodium hydroxide. Then what do you get? Well, actually you swap partners. It's like a double replacement. Sodium goes to chloride, right? And we know that's soluble. Well, what does hydrogen and OH make? HOH. No idea? How about starts with a W? Water. Okay. And that's characteristic of all acid-base reactions, right? This is that plus that plus that plus that. Okay. And these are all aqueous. So this one gets together with that one and makes that. And this is the net ionic equation for an acid-base reaction. Right? It's always hydrogen plus hydroxyl yields water. And that's the driving force. Because we haven't discussed equilibrium yet, but this is where it wants to be, right here. It doesn't want to be over here. So it drives it to water. That's what drives the acid-base reaction forward. It's the formation of water.
Hydrochloric acid contains hydrogen ions and chloride ions in aqueous solution. Sodium hydroxide contains sodium ions and hydroxide ions in aqueous solution. When these two solutions combine, a neutralization reaction takes place. In this reaction, hydrogen ions from the acid and hydroxide ions from the base combine to form water molecules. The sodium and chloride ions are unaffected and remain to form a neutral sodium chloride solution. Neutralization can be summed up by this simple ionic equation.
I don't really got the expression. What I like is Ocean's 11. Right, when the guy comes out of the sewer, it says, "We're in Barney." I say, "What is Barney?" "Barney Rubble, trouble." Never mind. So for an acid-base reaction, you have to do the same thing when you conduct a reaction, stoichiometry for acid bases. It's just that now you've got a different dynamic, because instead of forming a precipitate, you're forming water. Okay. And it really doesn't matter how much water forms. Okay? Because if you're in aqueous solution, let's see, what's the molarity of water? I used to know. It's like 30 or 40 molar. Right? Put a little bit of extra water in there, who cares? So when we do an acid-base reaction, we're usually, not always, but if we want to know when the reaction is complete, right? When all the hydrogen and the hydroxyls get together and make water, and there's nothing left over, or maybe there is an excess, right? An excess of hydrogen or an excess of hydroxyl left over. Then what we need to know is what's their concentration and exactly how much are we adding. So that's where the skill set of titration comes in. When we titrate, we take known volumes of acid and base, and we mix them together. Usually one of them, for instance, acid, is contained down here with maybe a stir bar to keep it mixed. And this will have your acid in it. Okay. Then we have a device called a burette. And it's marked off in milliliters, from 0 at the top to usually 50 at the bottom, and then tenths of a milliliter in between. And you're able to control how much you add. So what you do is, as you're stirring this on your stir plate, you have an indicator in there that is a certain color or not when it's acid, and then it turns to a different color when it's base. And you know exactly when that change occurs. That's where you stop and read off the amount of volume that you delivered. Okay. Now you know how much acid, how much base you delivered. I'm sorry, I didn't make that clear. How much base you added to a known volume of hydrochloric acid. And remember, if we know the molarity of acid and the volume of acid, and at the point where they're exactly equal, then the number of moles of acid equals the number of moles of base. In this case, that's true, because we've got one hydroxyl and one hydrogen for each molecule. It gets a little more complicated if you put sulfuric acid down here, where it has 2 hydrogens for each molecule, H2SO4, and this one only has 1 hydroxyl. Then you got another dynamic, and then you need a balanced equation to help you out. But the principle's the same. You add enough until you reach what's called an end point, which is very close to, if you're lucky, with your indicator, very close to the equivalence point. The difference between is the equivalence point is exactly the stoichiometric point at which acid and base are equal. And the end point is the point at which the indicator says you're really close. So that's what these statements are trying to say. You can determine the equivalence point for this type of reaction. But what you need is a pH meter, and you measure the acidity as the reaction proceeds. And you draw the curve, and then you find on the curve exactly where the equivalence point is. If you've only got 1, 2, or 3 reactions, that's okay. But if you're in a chemistry lab or a soil testing lab like I was, and you're doing 200-300 of those a day, right? You need to use an indicator, and endpoint's close enough. Or if you have automation now, maybe it'll do an automatic titration, and you can just set it up and go do something else. But that's an acid-base titration. Titrations are built upon the concept of equivalence. If you add something here into something here, when you reach the end point or the equivalence point, something is equal to something else. It doesn't have to be acid-base. It could be a precipitation reaction, right? We'll use that in the second semester, like I said earlier, with sodium, with silver chloride indicating our endpoint. But all of those are titrations. This is an acid-base titration. Oh, good. For the titration of sulfuric acid and sodium hydroxide, how many moles of sodium hydroxide are required to react with 1 liter of 0.5 molar sulfuric acid? In that case, you need this balanced equation. So here's your sulfuric acid, there's your sodium hydroxide, there's your water, and there's sodium sulfate. I didn't mention earlier, but an acid plus a base yields water plus a salt. In chemistry, that's the definition of a salt. You combine the cation from the base and the anion from the acid, that's a salt. It doesn't have to be sodium chloride. It could be any combination of calcium, any combination of cation and anion from an acid-base reaction. So once our equation is balanced, then we can do some stoichiometry, like 0.5 moles of sulfuric acid. Let's see, at 0.5 molar, let's see, 1 liter of this is 1 times 0.5 is 5 moles of sulfuric acid. Okay. And then we do dimensional analysis, right? 0.5 moles of sulfuric acid. And then we want to convert it into sodium hydroxide. So we have sulfuric acid here, sodium hydroxide here. Right? Coefficients say what? That's 1. This is 2. So we need 1 mole of sodium hydroxide to neutralize 0.5 mole of sulfuric acid. And the question is, how many moles of sodium hydroxide? There it is, 1 mole. Okay. That's one way to do it. And that's a surefire way to do it. There's another way that chemists use because it's quicker once you get used to it. It's called normality. Let's see, do we have that in this discussion? Because I don't want to burden you really if it's not here. No, we don't. Good. It may be in your book, though. Discussions of normality. All right. So redox reactions, they involve transfer of electrons. And they're called that oxidation reduction because oxidation means something. The electrons are transferred one way, reduction means they're transferred the other way. So what happens when reduction occurs and what happens when oxidation occurs? These are examples of transfer of electrons. Sodium metal and chlorine gas, when they react, the chlorine gains electrons and the sodium loses electrons. The electrons are transferred from the sodium to the chlorine. That's a redox reaction. We don't say ox-red, oxidation reduction. It just doesn't sound right. So we say redox instead. But in order to do it, we have to be able to calculate the oxidation state for each of the elements in the reaction. And that way, it's a way of bookkeeping for electrons. So you know how many were here. Now you got this many over there. Okay, they transferred from here to there. And that's all it is. It's just for bookkeeping. So we say oxidation state of an atom as an element is always 0. So if we said this, sodium metal, the oxidation state would be 0. Or if we said this, chlorine gas, the oxidation state for each of those chlorine atoms would be 0 because they're both elements. And then when they react, right? So we're going to have 2 here, we're going to have 2 there. Okay, that's losing its kick. Where's your cat? The oxidation state of monatomic ions is the charge on the ion. So if these ions, sodium ion and chloride ion, this is a +1 and this is a -1. So the oxidation state on this sodium is +1. The oxidation of that chlorine is -1. Okay. When oxygen is in a compound, say water, the oxidation state on that oxygen is -2. That's what oxygen prefers. The only time that it's not -2 is when it's in a peroxide. So anytime you have an oxygen bound to an oxygen and to something else, see your medicine cabinet, You got 3% hydrogen peroxide. Both of these together are -2, so each one is -1. That's the exception to the rule on oxygen. When it's a peroxide, they're -1. Hydrogen, in any covalent compound like this one, hydrogen is always +1. Right, so that makes sense. 2 times +1 is +2, balance is a -2. The only time that hydrogen is not +1 is when it's bound with a metal. For instance, let's do aluminum hydride. Aluminum is going to be 3+. Each one of these is going to be a -1. That's the exception for hydrogen when it's bound to a metal. But when it's covalently bound to anything else, it's always +1. Now, why do we need to know these rules? Because some of the elements, you don't know what their oxidation state is until you calculate it. And you can't calculate it unless you fix some of the components, some of the elements to begin with. And these are the ones that are fixed. Fluorine is always -1 in a compound, always -1. With that information, now we can say that the sum of the oxidation states in a neutral compound is always 0. So for instance, +1 and -1, that's neutral. The sum of the oxidation states in a polyatomic ion, say like nitrate. So if you sum up the oxidation states for all of those atoms, it has to be -1. So let's see what it is. -2 for the oxygen times 3 is what? -6 total. Okay. So this nitrogen has to balance that -6, but we've got to hold a minus out for that charge. So really, it only has to balance at -5. So it's +5. And check yourself. If this is a -6 total for oxygen and a +5, that leaves you a -1. So that's how and nitrogen will vary, right, depending on the compound, like many others will. All right. So what are the oxidation states for each one of these? Well, we didn't cover it. Well, we sort of did. I'd like to add alkaline metals. They're always +1. Alkaline earths, they're always +2. Boron, aluminum, and gallium, they're always +3. So that means potassium is +1, oxygen's -2. So we say 2 times +1 is +2, and -2 times 7 is -14. And a +2, that means -12 is what we have to balance. So -12 is balanced by the +12, but there are 2 of them, so each one is +6. Okay. And you can do that with anything. Carbonate, the carbonate ion, we have to balance the charges, but we've got to be sure and hold out 2 minuses for that charge. And if we do, carbon is a +4 and oxygen is -2. You know, work it out. You'll see it's right. Manganese 4 oxide, there you go. Phosphorus pentachloride. In this case, the best way to work out the charge is not against the chloride, but against the phosphorus. So the chlorine is going to be like its little brother. Fluorine above it, -1, chlorine to be -1. And like I said, this is a bookkeeping scheme. This doesn't mean that there's a charge, because these are 2 nonmetals. Right? We know that those are covalently bound. Right? They're sharing electrons, they don't transfer electrons. This is a bookkeeping scheme. So if this is -1, phosphorus has to be +5. And fluorine is -1, so sulfur has to be a +4 in that case. we have to be able to calculate these oxidation states in order to determine how many electrons move and where do they go. Okay, so what does oxidation reduction mean? That's an I and that's an I. Oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. Right. If you ever have trouble, remember that. Oxidation is loss, reduction is gain. So, when we write these equations, we can say one element or one compound is reduced by gaining electrons, and somebody else has to be oxidized. Oxidation and reduction always occur together. The number of electrons that move away from something have to go somewhere. Right? Otherwise, you have electrostatic charges. We don't have those in bench chemistry. So, there's a trick, and this is a good example. When you have an element right here on one side of the equation and it ends up in a compound like this, that's an oxidation reduction reaction. Why? Because this one's zero and that one has to balance a charge against the chlorine. So it's got to be a change in oxidation state. This one we'd have to calculate. Let's see, I think that's +6. This one's also +6. That's a -2, that's a +1. So there's no oxidation change here at all. This is not a redox equation. This one, yes. See that copper? That's a 0 oxidation state, but over here, it's in a compound, right? It has an oxidation charge. So yeah, A and C are both redox reactions. Okay, now the question is, and we've got to introduce another term or two. Whenever you have an oxidation reduction reaction like this one, let's use this for an example. Zinc plus 2 hydrogen chloride yields, that's hydrochloric acid, excuse me. Zinc chloride plus H2. I'm not going to write in the phases because it takes up too much room. If this one's 0, that one's -1, this is +1, this is -1, this is +2, that's 0. Right? Where do the electrons move? Well, this zinc has what? Lost 2 electrons. Right? I like to draw tie lines. So this is a loss of 2 electrons per zinc. Right? So how about this chloride? No, chloride didn't change. Hydrogen changed. So wherever there's a loss, there has to be a gain. This hydrogen is a +1. Now it's a 0. So we have here a gain of 1 electron per hydrogen, but there are 2 of them, right? Times 2. So there were 2 electrons gained and 2 electrons lost. That's important, right? This is an oxidation, this is a reduction, and the number of electrons lost is the same number of electrons gained. Okay? Now, we can say this one was oxidized. This one was reduced. So whichever one is oxidized is responsible for the reduction of the other one. That makes this one the reducing agent. And this one, the oxidizing agent. Okay? If it's reduced, it's the oxidizing agent. If it's oxidized, it's the reducing agent. Now the other one, this one right here, that's an interesting one. 2 copper 1 chlorides yields copper 2 chloride plus copper. So that was 0, this is -1, this is +2, this is -1, this is +1. So how do we figure that one out? This is a special kind of reaction. Make room here. This is called a disproportionation reaction. Disproportionation reaction. What that says is this copper goes 2 different directions. Right, there are 2 of them. So one of them goes that direction and the other one goes that direction. So we can say this one goes to here, and when it does, it's oxidized, loss. 1 electron per copper. And the other copper goes this direction. This is gain. 1 electron per copper. Okay. Maybe it would be easier to rationalize if we wrote these separately, like copper chloride plus copper chloride. Use those. Then they would be more visible as separate reactants. This is one way that refiners use to purify copper. If the ore is copper chloride, all you have to do is heat it up. And it produces this plus this copper. So you get part of the copper out that way. Then you take this and do something else to it. Okay, so those 2 are redox reactions. And these are just step by steps. I like tie lines. These are steps for balancing equations using redox. So if you know you have a redox reaction, sometimes it's more efficient to balance the electrons first. And then go ahead with your budget, finish balancing the equation by previous means. All right. I'm already 45 minutes over. So I guess you guys are okay with sticking around.
I'm kind of reading this and then out of document content, but.
Okay. Balance the reaction between solid zinc and aqueous hydrochloric acid to produce aqueous zinc 2 chloride and hydrogen gas. We've already done that. This could very easily be balanced by our budget method. Right? But what I want to show, let me see. Yeah. What I want to show is that you can also balance it by the redox method. So here we've written zinc and hydrochloric acid, and we've got these ions over here and hydrogen gas. So what are the oxidation states on each one? There you go. We did that before. And then draw your tie lines so that you can account for the electron movement. And in this case, we've got 2 electrons moving from here to produce that. 2 electrons were lost from this zinc to that zinc ions. And in this movement, we've got 1 electron gain for each atom. Chlorine remains unchanged. So let's go back, draw our tie lines in again. Now we need to balance the electrons. So what we need is 2 times this. So what does that mean? We need a 2 here to get 2 hydrogens. And we've already got a 2 here, so we don't have to change that. So that 1 change is all we need. And we've got balanced electrons. And now we check to see ourselves if the atoms are balanced. There's one zinc here, one zinc there, two hydrogens there, two chlorines there. Oh, we need two chlorines over here. Oops, sorry. Too far. So we put a 2 right here. Now we're balanced. Balance the electrons first, then finish off the atoms. That's a very simple example. There are more complex ones hanging out there in the ether. But I've kept you long enough. Well, next Tuesday, we'll do a review using that document. And we also have a lab.